Hello everyone and welcome to a new episode of All Things IDA. In today's episode, I'm going to be repeating a talk I did in REcon in 2012. Now this talk has been lost, so to say, it has never been released, and I think it's fun to go over it again just for posterity. Now we are in 2024, there's so many other ideas, more modern ideas, but still I think this is useful. Maybe you get some inspiration if you want to start from scratch and design something like that. Before I start, I have a small story to share. Of course, you can simply skip that in the chapters below. With that, let's get started. This talk is about the internals of the Bochs plugin in IDA. Now, in the past, I explained Bochs and how to use it in different operation modes, and I did promise that I'm gonna revisit and explain the internals of Bochs. So this is the talk where we go deep into the Bochs plugin, how it works, and so on. Now, this is the first assignment I got when I joined Hexrace. I remember back in 2008, Ilfak was driving me from the airport and we were having a 1 hour drive from Brussels to Liège. And during that 1 hour drive, we were chatting and discussing about that plugin. And for the next 3-5 months, this is the only thing I did. And then it was released with IDA. This plugin is really special to me because it just simply reminds me of the period when I first moved from my home country to Belgium, and I remember experiencing long days where the sun used to set in the summer around 9:30, even 10 sometimes. And I was really working long hours, but it was really fun. So that's the story. And now let's deep dive into the inner workings of the Bochs Debugger plugin. So this was the first task I did, and I started in August, and by October 2008 we started talking about it and a small demo how it works. And here we're talking in IDA 5.4 in 2008. So that's the first demo in October, and then in November it's alpha. Now we're ready to test it and so on. And then it went live in 5.4. So the talk that I presented in REcon in 2012 talks about general design idea on how to have a specialized operating system that runs snippets of code or a single file. So as opposed to having to need a large operating system like Windows, the whole Windows VM, instead the approach we took is let's just simply try to create a disk image per input file, whether the input file is BE file or shellcode or snippets of code. Like this, we have minimal disk space needed, and also we can control the emulation environment while relying on a full-blown emulator, as we shall see. We'll be using Bochs. I'm going to be using the slides as reference and not necessarily following them to the details. Instead, I'm going to take the opportunity to demo directly what I'm talking about. So the motivation behind this is the need to be able to emulate some pieces of code or startup of a packed binary and so on with ease. Static analysis alone is not necessarily great all the time. These days, people might resort to emulators, symbolic execution, even debugging in a real VM and so on. So this is really the motivation behind the Bochs plugin. So in practice, we should be able to emulate shellcode, packed PE files, even code snippets, and 64-bit shellcode as well on 32-bit hosts. That will be possible because of the underlying emulator we're using. And most importantly, all those practical uses, the goal of the Bochs plugin is to make this accessible as fast as possible and make it more convenient for us being integrated in IDA. As overview, this system is composed of multiple components. First, we need a programmable emulator, and for that reason we used Bochs. We need a driver program, and this happens to be the IDA Pro plugin. And by driver program is the orchestrator that talks to the emulator and also prepares the disk image and be the middleman between the emulator and the emulated code and the user interface. So that's the driver program. And the third part here is the code to emulate, whatever its nature is, as long as we have instructions. We needed an emulator that can give us a bunch of facilities. So we need to be able to start, stop, or suspend the emulation, to be able to create disk images programmatically, and also to be able to single step, trace, change registers, read registers, add breakpoints, and read write memory, whether physical memory or virtual memory. These are the needs that will help us create the emulation environment to emulate all the targets we discussed. If we visualize this system, we start with input files. Either they are structured, for example, PE files, shellcode. Then the driver program will go through the image creation. This is a disk image creation. This is what we will feed to the emulator. And the image should have enough code to create that environment for the input file to run. So as well as we said, we can think of the image creation as if we have that dedicated operating system. And then we'll have that runtime environment or image execution engine. This is where it will have a small operating system inside it that gives the semblance of the target operating system. So we're gonna mimic Windows, for example. And that as well will have some knowledge and knows how to talk to the emulator. And this whole system starts from the input file, create the image, run the image. As the image runs, it goes through the master boot record. It has a small operating system or kernel. We do some API and operating system emulation. And then if the user interacts, say, single steps and so on, we can send the commands to the underlying emulator. If we want to read the memory, same story, add breakpoints, and so on. So when we create a disk image that we are booting using Bochs, we have to put a bunch of things to make that disk image viable. We have to have a master boot record that will set up when it executes, it will set up the GDT and IDT and page table entries. It will switch to protected mode and do all the necessary things to make this image viable. And the disk image creation starts from something. It could be the PE file or the database itself. So in Bochs, as I demonstrated in previous videos, we can go to operation mode. If we set IDB, that will simply take the IDB contents, however it is mapped, the segment start, segment end, all the segments, and that's what will be used to dictate the virtual memory layout in the emulated environment. If it's a PE file, the memory layout is dictated by the PE file, mimicking the real operating system PE loading process. Now, the virtual memory management is not implemented inside Bochs virtual environment. This is for simplicity reasons. I didn't want to write so much code that runs inside the emulated environment. Instead, I decided to implement most of the code in the plugin itself. And then anything we do with respect to virtual memory, the side effect is simply a physical memory write. For example, let's say we want to allocate memory. What is a memory allocation? At the lower level, a memory allocation is simply going and patching a page table entry with the appropriate settings. And so I can do that in C++ in the plugin, and then simply record the changes. What are the physical memory locations we need to patch in the virtual environment? So any memory operation really is just a physical write. So at the higher level in the plugin, I have things like map many pages and map a single page and so on. And then after that, every function of the functions I mentioned, they will eventually call serialize, meaning record what did you want to write, at what physical memory, and what are the bytes you wanted to write. That's all it is. Then we send those physical memory writes back to the virtual machines, and like that we have allocated virtual memory. Let me show you what I'm talking about. So here I have Wismo 64exe. I just packed it with UPX, and now it's packed. Let's load it into IDA. Now again, the packer is not important. The idea is to illustrate the design of this operating system. So it is loaded. Now I'm gonna go to the debugger switch and select the Bochs debugger. And I'm gonna go to the debugger options, specific options, and also talk about the options. So we discussed the operation modes in the past. Here just to show you some things. For example, 64-bit emulation, stack size, maximum memory. So remember those attributes because this will affect the image creation. And here we have an option, delete image file upon session end as well. We're gonna explain what those mean. So it seems configured correctly. I'm gonna hit run. Now it took a second, and then now we are suspended in the debugger. Why did it take a second? Because this is the time where the Bochs plugin parsed the PE file, mimicked the dependencies. So here let's talk about the dependencies. So here, for example, these are modules, and These are what that program requires. Here, for example, we have as well some DLL that you never really see in a real environment. And all of these are pulled and decided by the plugin itself in the component that does the image creation and the input file loading. So if we go to the IDA installation plugins and we go to Bochs, so we have additional files here where we can configure Bochs. And we have bochsdbg.exe and bochs64. This is the 64-bit minimal kernel that looks like Windows that will also be assisting the emulation during runtime. So if we switch back to the emulation environment, we're suspended here. We have the actual virtual memory mapped. If we press Ctrl S, we see all the segments. This is all emulated and running in the emulation environment. If we keep this running and just simply switch to the disk here to file system, we have additional files that got created when we hit F9. If I stop debugging, they're gone. We're back to nothing. So let's keep them and say don't delete the image so we can take a look at them. So let's run again. So again, the image creation process kicked in and it created a disk image. Now let me stop debugging, and now we have those available for us. So we have the Bochs image. If we look at it, this is, let's see how big it is. It's just 1 megabyte virtual machine, and this is the contents. It has everything it needs to run that packed program inside Bochs. We're going to talk about the components of that. Additionally, there is this file here, which is the bochsrc file. This is Bochs specific, and this is also the image creation part of the Bochs plugin is what creates the memory. It detects how much physical memory it should allocate. It points to the image we created. So this whole file is generated. And all the other stuff, we can add things, remove things, and so on. But the minimal is at least how much physical memory and where is the image that we need to run Bochs with. Now, if you take just those two and feed them to Bochs outside IDA, you have yourself a dedicated operating system that can run that PE file. But it's not as simple as that, because we need some kind of execution engine that knows how to handle APIs, single stepping, and certain aspects of the system. So that's where it's a comprehensive system, and we just covered the first part of image creation. Before I switch back to the slides, I'm gonna run it again and just show you other things. So let's go back to the modules list and talk about the dependencies. So how do we have kernel 32, for example? When we load the input file, we parse the imports and we deduce what DLLs we need. Then we go to the disk on the host and mimic that DLL by creating a fake DLL with the same exports. So like this program will not complain about a lack of certain API. If we dig deep into one of those APIs, we can see that it doesn't have any code. So here at vectored exception, it has very much dummy code, just like move AX something, and it's going to go to undefined API call. That's how it's implemented. If we pick something else, it's going to be the same story. What about picking load library, for example? Well, load library is a bit special. It goes to the operating system where it handles load library. So it goes to the Bochs sys. I call it operating system because it is a minimal operating system. And here in the modules, we do have the operating system loaded, and this is coming from here. So we will be reversing this one in a shallow manner just to discuss the internals. So but if we go over that minimal operating system gives us some primitives that are enough for us to do the runtime emulation. So we have things to allow us to call into IDA. This is a mechanism where the guest, the emulated environment, can interrupt, call IDA. IDA will do some work on the host and then return back to the environment, the emulation environment. If we need to allocate memory as well, we have this facility here, Bx virtual alloc. Follow it. So here, the virtual allocation, it has some code, but as well, it goes and asks IDA plugin, the Bochs plugin, to do the allocation, and then it returns back to the host. Now, the virtual alloc, for example, if we go back to kernel and search for virtual alloc is redirected to the Bochs operating system. So here, virtual alloc EX has not been redirected. We can simply reconfigure it to redirect. So let me show you. Here, let's take Python for example, and this is how we can configure what is handled by emulation, what is stubbed, what goes to the host, what goes to IDA Python, and so on. So here if we search for virtual lock, and here the file is called API kernel32.py. So API is needed prefix and then the DLL name. And here what we're telling the emulator, the Bochs plugin, that kernel32.virtuallock should always be redirected to the operating system virtual lock. And in turn, the operating system's virtual lock is gonna do an IDA call to do the allocation. And so here, for example, we have all of those redirected. These are the lower level primitives that are always redirected to the operating system. But for example, suppose we want to do a load library. We tell it that load library ex is this, and basically here the entry is the Python function name. So we bound kernel32.library.ex to a Python function called k32.loadLibrary.ex. And here we use some facilities in either Python and the Bochs API to implement that. And so here we say Bochs get parameter number 2, which is the H file in this case, and so on. And like this, we supplement the emulation via a script. For example, beep. For beep, in kernel32, all we do is just take the parameters and print them, nothing else. And update the register, which will be updated in the emulation environment. So now that you've seen the whole picture real quick between the physical disk image, the stubbed APIs, the script backing for the APIs, and so on, let's see if there are other details. The startup configuration file. So this file here is startup.py. It will tell the emulation environment which DLLs to stub and which not to stubs, what environment variables we need to set up when we start the emulated environment, and also if you're running non-Windows, then where to find the DLLs. So hey, I'm gonna give you this DLL, but map it inside the virtual environment as such. So these are all special directives that configures the Bochs emulator, and we can have so many things in the startup. And then we have, as I said, per DLL configuration. Like this, we can tell it how to redirect things, say kernel32 get module file name, where's the implementation, get module handle, load library. These are the primitives needed by most PE packers, and these are provided. And those are enough for us to step all the way from the packed state to the unpacked state. And similarly, if we have, for example, user 32, we're gonna see, for example, here as a demo, message box is simply mapped to the Python function message box, which simply goes and execute this Python code, IDA Python code. If we look in the emulation environment to message box, here this is message box. If I go to the modules and select message box, message box is gonna be handled by the script here. How is that translated to the emulated environment? Message box is gonna do an IDA call. That's a way to transition from the emulated environment into IDA Python. And then when this finishes, to return to the caller. And as well, since IDA Python decided to change the register value, it will simply transfer the register value from the script to the emulated environment, for example. Now, this is the only function that is in user32 that is backed by IDA Python. So if we pick any other random method, say getString, it does nothing. It just simply goes and does not call into IDA or anything. And those functions are special functions. So for example, Bochs UndefinedApiCall, it looks like no operation, but we intercept those and act accordingly. Let's go back to message box. Message box does an IDA call. So it interrupts execution, goes to the plugin, to IDA Python, and returns. How is it implemented? Well, it's also NOPs, but it's not really NOPs. In reality, we have control breakpoints. So we have a bunch of control breakpoints, which we intercept. So these two breakpoints at the minimum, these are what we catch IDA call and other needed special points in the execution in the virtual environment. All right, so this is the configuration files I showed you. This, for example, the beep method, as I explained. Dummy API stubs. for most of the functions that we do not support, we create a correct stub on 32-bit at least. We have to purge correctly. So here return 12. This is important. Then even though this is an empty stub, most cases it will not be used anyway by the unpacking process. So if we go back to the packed program and whatever it's calling, it's not gonna be calling anything more than what we provide as primitives. If I run this program and let's go to kernel 32 virtual protect, add a breakpoint here, and let's also go to kernel 32 load library because there will be import reconstruction as well. Let's put breakpoint and let's go to get proc address, and then that's the entry point here. But we will first stop at get procedure address and load library for sure. And this is enough for the unpacking process. So if I let it run, okay, here we have our first load library, and this is a 64-bit program. So RCX is the library name, and here if we single step and step over this one, so again IDACall is nothing, it's not going to do anything. But if I run to cursor here, even though this looks like nops, this will eventually call IDA. IDA will do the stuff needed and return the register's values changed to be giving us the base of kernel 32. So let's right click, run to cursor, and here this is the image base for kernel 32 in the virtual environment, and it will satisfy the packed program. It will also call get proc address. So the packer will also call get proc address, put a breakpoint here, let it run. This is get proc address. RCX is gonna be the image base. RDX is gonna be the API in question, so it's gonna resolve heap pre-alloc and so on. So if I let it run after get proc address, we will have into RAX pointing to the proper thing. In this case it's a forwarded function, so it went and gave us the NTDLL value. So all of this is supported by the emulation environment. Let it run, it's gonna keep calling get proc address and the load library and so on. It's changing memory protection, doesn't matter, and transition to the entry point. If we step one more time, now this should be familiar to us. This is the C runtime startup code here. This is the program now unpacked, and this is the original entry point. Let's continue. If I do the same but switch the emulation environment from PE mode to IDB mode, and in fact I can just go to the PE file itself. Let's go to the entry point and just capture just some pieces of code, doesn't matter, just to create a binary file, x.bin for example. I took some bytes here, so I took 46 bytes. Let's load them into IDA, and IDA doesn't recognize this as anything but a binary file. We just have to make sure we're choosing the proper architecture. Is it 64-bit? Yes. Okay, let's rebase this to some address. Now this is piece of code. Of course it's not gonna work 100%, at least we can go a couple of instructions maybe here. So we're gonna put a breakpoint, we're gonna select Bochs, and Bochs automatically say, okay, I don't know, it's a PE file 100%. Of course it's not, so it's just the IDB mode, whatever we have in the database, and we're gonna do that. So IDB 64-bit emulation, and let's run it. Same story. Bochs plugin went through the image creation mode, created the RC file, the disk image file, and it started Bochs behind the scenes. If we check the attributes here, the command line, the plugin in IDA executed Bochs, passed it the image file in quiet mode, and in particular it executed the bochsdbg that will give us debugging facilities. If I issue the same command line, I should be able to do this outside IDA as I told you. Let me show you, and let's stop debugging, and this is the RC file. Let's go to program files, Bochs, and let's take the path for this one, and now let's just simply say -f x.bin.bochsrc, and that's how you would run Bochs by yourself outside IDA. But as I said, that won't be necessarily enough. You need an additional logic. Alright, we're gonna dig deep into the MBR in a bit. So the loading, we parse the file, we have virtual memory operations, we serialize them, we write them to disk. We're gonna discuss the file format of the disk. So we're gonna look at the disk image, the master boot record. We're gonna look at the embedded kernel. This is the Bochs or Bochs x64. We'll also look at the GDT IDT serialized stuff that we need. And then as well, all the rest, if we want to really simplify the whole thing, we can think of the image that the plugin creates as if we did a hibernation in Windows. You hibernate, you flush the image state to disk, and then you boot again and you resume from where you started. We can think of this whole design as if we're doing hibernation. We set up the whole environment and then we boot, restore the memory contents, and execute at the last point of execution. So if we look at the disk image format, it has the boot code. This is 16-bit code that will do a bunch of things I will discuss. Then it will have the whole disk image, basically all the streams like the PE file, the dependencies, the Bochs operating system, and so on, and some additional metadata needed by the plugin. So we're gonna now look at the disk image itself. This is the disk image. You can see some artifacts. These are coming from the operating system. We see PE files, everything that is needed. So I already did some reversing on the disk image, but just quickly to illustrate, let's suppose I haven't went through this. How would we do it? So the Bochs plugin itself supports 3 modes of operation. It supports PE file, shellcode, and a disk image. So if I run IDA and give it the RC file, the Bochs RC file, which is simply designates the configuration of the virtual machine, IDA will be able to load it starting from the boot record. So if I start with the Bochs RC file, I'm debugging the Bochs MBR part. So if I open that disk image, I'm gonna be basically debugging the components of what the Bochs plugin creates, in particular the boot code. So if I disassemble this file, IDA detects it, and it will preload the database with the first sector. So if we go here and here, it will preload it with this piece of code here. We see the jumps and we see the calls. We'll see those. So here it is. This is the same as this. IDA pre-populated it, but since it's the MBR starts at 7C00 and 16-bit mode, it's pre-populated. You can see all the calls here and so on. And this is part of the operating system. This is coming from the IDA Bochs plugin. Okay, so I have this whole thing documented as well. So the disk image, what it has, we're talking that the disk image has an MBR, followed by the MBR, it has a bunch of streams and so on. So let's skip here. So the boot process, which is part of the disk image, starts by clearing the screen, loading boot sector, displaying loading message, going to Unreal mode so that the 16-bit code can access up to 4 gigabytes of physical memory. We load all the serialized contents, so the PE file, PTE entries, and what are the physical values to set those PDE/PTE entries, page table entries, page directory entries, and then load kernel. So this is the same as any other Bochs image, but it's not documented. So this Bochs disk image, I simply documented it based on the slides. I'm in disk image mode, and I'm gonna be debugging Bochs Debugger with the Bochs plugin here. And we are in the MBR, and we should see now, this is the output window. So it already executed the BIOS code, BIOS loaded the MBR, and this is our MBR at 7C00, 512 bytes for the first sector, and there will be another sector. So this part is what loads the objects, meaning all the stuff needed from the database have been already serialized. They'll be needed in the VM, so it will also load the page table and page directory entry configuration. We'll see. So first thing here, clears the screen. It will use interrupt 10, set video mode, and then it will load the second sector. So here we use the BIOS interrupt 13 to load the second sector, and then as well, additionally, it checks the beginning of the second sector if it has that special signature. So let's just run it here. It loaded it. Now it's gonna call display message. It's gonna display loading here. It will enter Unreal mode, and it will load the objects. So we will look at the objects or the format of the image file. So read, compare for the signature, and as well it will just simply load every single object. So now here, as it loads every object, it will display ... So let's wait for it here. Did it fast. If we were emulating a crash dump, for instance, that can be many loading dots, and it might take a longer time than a simple few kilobytes executable. It will display the message debugging with IDA with a certain color. Debugging with IDA. And it will load the kernel, either Bochs. It's gonna load either Bochs 64 or Bochs 6, which have been already baked into this. So they're already part of the image. So it's simply gonna transfer to that mini OS. So here it's gonna enable protected mode here in CR0, and it will do a far jump with the new selector to enter 64-bit mode. Here already now we are in 64-bit mode, this 64-bit code, and this code is really if we disassemble one of those DLLs. So just a side note, as they ship with IDA, those DLLs don't have MZ header because they have always been flagged as malicious. So they are patched with HR instead. And so just took a copy and put back the MZ so I can load it in IDA. And you will see that this operating system here, R0 entry, is the same as that code we see here. And this code eventually will transition to the entry point of whatever target we are debugging. So this is the whole workflow of that boot sector loading the continuous objects or streams inside the disk image and transitioning to the kernel code and then to ring 0 and ring 3 afterwards. So let's take a look at the file format. For the file format, let's open the 010 editor and open that template. So it's a very simple template, and the format is documented in the slides. One you want, you can take a look later. But eventually what we have is the first sector followed by the second sector, and then we have some magic constant, and in 32 designated whether this image is to be loaded with 64-bit OS or 32-bit OS, how many objects, and then a loop for the object count, loading sub-objects. So every object has this header part. So let's take a look. So we can load, for example, this is the disk image. Let's load it. And we should be able to run the template. And now let's take a look. So we have the boot sector, first sector here, second sector to continue the code of the boot sector. We have the magic constant, hex raise box. It's a 64-bit image, one object, and then there's other sub-objects. So for example, here now we have size, where it should be loaded physically in memory, and the contents. So those with small sizes most likely designate page table entries or page directory entries. That's how we are kind of coming out of hibernation. This is same story, size 8. So depending on the serializer, eventually we will find bigger objects. So still small objects could be related to page configuration. So here, for example, could be part of a PE section. For example, this looks like code 48, P8, and so on. So that's the format. After the boot, as we said, it then jumps into the kernel, and the kernel jumps to the target, which is the ring 3 code. So let's take a look at the kernel. So this is Bochs DLL. I also disassembled it a bit, and we can talk about some of its characteristics. So the entry here sets up GDT, LDT, IDT for interrupt descriptor tables. That's what will let us emulate in threes, handle exceptions, page faults, translate them to Windows looking exceptions. So in the kernel, we set up IDTs for exception handling, for example. We will have as well implemented the exception dispatcher. Let's see, exception. So here, for example, the common interrupt handler, we use Windows related context structure. we have to be imitating Windows. So we have the context of Windows. We convert from raw CPU exceptions to Windows exceptions. So we populate all the registers from kernel mode and put them in a context structure. And then we return back to user mode after we handle the exception. There should be multiple handlers. So for example, in 01 handler, in 03, we have here 0E, 0D, one of them is page fault, and so on. So we populate them. So each one of those is pointed by the IDT. Let's explore a bunch of functions. So we looked at virtual unlock. It does nothing really. All it does is calls to IDA. IDA gives it a result. And we do some little things here. We just call this interrupt. Let's see other functions. Virtual protect, same story, calls to IDA. IDA will change the page table entries and return back. Virtual free, all of them, they don't have real implementations. They're all called to IDA, all of them. Exit process as well will call BxExit process, which will also call into IDA. And when we call into IDA, it will be receiving special numbers as arguments. So every time we see a Bx call to IDA, RAX is loaded with a special number that's recognized by the Bochs plugin in IDA. Now for the 32 bits, it's going to be similar story. Continuing here, let's see what we missed. So kernel initialization, how we convert those exceptions, so divide by 0, single step, and other things. So the kernel allows certain interrupts to be called from R3 as well. All interrupt handlers share the same stub. We've seen that. The R3 interrupt handler, all of those interrupt handlers go to that common code. And here it is, for example, interrupt E, interrupt D, they all go to the same interrupt handler. Then we save the registers from ring 0 so that when we return to ring 3, it will receive a context. So this is ring 3 exception dispatcher. But as well, it will convert the raw CPU codes to the Windows exception. So it will fill in an exception registration record, and one of the members is going to be the context structure. And also the kernel will properly dispatch the exceptions via emulating the structured exception handler chain list. So it will call every registered exception handler until one of the handlers say handled or continue searching and so on. As well, TLS dispatching is supported by this emulator. So because the original motivation is to trace backed programs, we try to make sure we implement most of the things that are used in packed programs, only up to the original entry point. So we don't support threads or windows or anything of that sort, like find window or window API or thread API, because they're not usually used in packed programs. So the packer stub usually wants memory allocation, loading the DLLs, changing memory protections, and maybe hiding some code in TLS callbacks, hiding the control flow via exception dispatching and exceptions. So same story, the minimal operating system, the Bochs sys, knows how to handle the TLS dispatching. Guest to host, this is what we said, the BxIDACall. The basic idea is we have a hidden control breakpoint. When it's hit, that breakpoint will inspect either EAX or RAX, and internally in IDA, it knows how to invoke the host function. So beep, for example, we have a special index for the beep, and we call a host call or IDA call, and then IDA knows what to do with that based on that special code. So here can handle breakpoint. This is inside IDA plugin, inside the Bochs plugin. We check for the handlers based on AX, which is the special identifier. If it's, for example, required to be handled by a script, we forward it to a script. Otherwise, we handle it internally. For example, virtual unlock, when the guest or the virtual machine calls virtual unlock, it gets translated to an IDA call and dispatched accordingly. So as we said, BX virtual unlock, the real implementation is simple. It will put into AX a special code, call into IDA. The Bochs plugin will intercept that, does the needed operation, so populate PTE accordingly, and then invalidate the cache or clear the memory in this case. And so, for example, a memory operation during runtime, we have the virtual memory manager code already aware of the memory layout. It will update the internal structures and register all the patches into a serializer, and then we upload the serializer data, all the side effects of changing memory protection, which will translate to write physical memory, and we invalidate the pages. So this basically is everything with respect to the code. Alright, so that was it for today. I hope you found this information inspiring if you want to design a small operating system or even debug your operating system with the Bochs plugin itself. Thank you, and I'll see you next time.